Okay, so now we're going to get into chemistry. And chemistry is defined as the study of matter and change in matter. This lecture is going to be looking at a type of matter called gases, and from one of the videos that I had you look at gave you an idea of what gases are, and we'll go over more of that. One of the things about this, I've always had a little trouble trying to figure out where to put gases in chemistry, because what we're going to be talking about primarily is not chemistry, but is actually physical properties and physical changes, which is not chemistry. But one of the things, so what I've found it is useful for is gases. First of all, were one of the first studied parts of chemistry. Chemistry is not all that old. It's really had its beginnings in the early 1800s, and gases were one of the first things that were studied in terms of chemistry. Now, it is the study of matter. So it was one of the first studies of matter. And one of the reasons they were able to do the studies on gases versus other things, because they could look at how gases behave. And why they could do that is because they had new things called barometers and thermometers, and that we just take for granted every day, and glassware. And so what they were able to do is collect gas and look at its volume, its pressure, temperature, and how much gas is there. And from that, a lot of actually elementary chemistry laws sort of were started. So we're going to be talking about the gas laws, and like I said, it's mostly it's really just physical properties and physical situations of gases. And we'll apply more of the laws especially the law, Avogadro's law, when we get to stoichiometry. Okay, so one thing about gas laws is that when the laws were first discovered, they had no idea that there were atoms or molecules. They just thought there were different states of matter, and they didn't have to be made up of anything in particular. So gas was just gas, liquids were liquids, and solids were solids. So the gas laws that we're going to be looking at, Charles' law, Boyle's law, etc., these laws were discovered in the lab, just looking at how gases behave empirically, as the way that we can view them. Okay, in the idea of the atom or the molecule really was slow going. It was first hypothesized, at the modern idea of an atom by Dalton in early 1800s, studying gases. But that idea of the atom really didn't take off. There wasn't any real need to look at substances as being made out of atoms, okay, or molecules. They could explain almost everything using other things to explain it. But eventually, in the late 1800s, it was realized that you could have that there was things that came from other things, like electrons, that we started to understand that there was probably things that made up matter. And it wasn't until 1905 when Einstein actually proposed, well, not only proposed, but actually proved in one of his famous papers, 1905, he came up with 4 of the greatest papers ever, including the theory of relativity and a couple others that which I actually going to talk about. And one of them was a paper had to do with Brownian motion. And a Brownian motion is as if you ever, if you look at it up in light, you'll see dust particles moving around, and they just seem to be moving around randomly, and they're not falling. Okay, they look like some are headed one way, some are hitting other ways, some are falling, some are rising, some are moving left, and that was called Brownian motion, and they really didn't know why that was caused that. And what Einstein was able to show is that those particles moving around were caused by other invisible particles that we couldn't see, and that's those invisible particles were referred to as atoms. So what we're going to do is we're going to treat gases as not something in the experiment world, but actually down at the molecular and atomic world. And so we're going to pretend that we're going to become really, really, really tiny, and we're going to go watch atoms and molecules move around, and then see how they behave. And obviously we can't do that, but you can do it in your head. So what we have here is assumptions based on the kinetic theory of ideal gas. And so first one is we have gas particles, and those can be either atoms or molecules, and we'll talk more about atoms and molecules in a little bit. But one of the things that we're going to deal with in this ideal situation is that gas particles do not have any volumes. And one of the reasons why we say that is because they're so tiny, and they never really bump into each other, okay? That we can just sort of regard their size as negligent, okay? Not negligent, but very, very, very small. But they do have mass, okay? So these point particles, whatever. So if you have a tiny gas particles like this, okay, this gas particle might weigh 20 AMUs, and why this one might weigh 100, but they both have the same size. So one of the things that you could actually look at is they have different densities, because so density is mass per volume. So all these gas particles have different densities. They all basically have the same volume, but different masses. And to move further along in what we're going to discuss now, is all our gas particles that we're going to talk about are going to be the same. So we might be just talking about this guy here that has a mass of 20 AMUs. And if you don't know what AMUs mean, we'll get to that in a little bit. It's just a measure of mass for atoms and molecules. So we don't want to deal with 2 different types of gas particles. We're only going to deal with one type of molecule. So like I said, we're going to assume, okay, this is assumption of an ideal, is that these gas particles never crash into each other. They don't have any attractions or repulsions for each other. They're always moving. Okay, they're always moving in a linear fashion. So not like that. Okay, they'll move straight. Okay. Okay, we always consider that they're in closed containers, a closed system, and are randomly spread about the container. Okay, they can and will interact with the walls of the container, but not with each other. Okay, when they crash into the walls, they don't lose momentum. So momentum is a velocity times mass, and so really we don't care about the mass here. Really the main thing, since they all have the same mass, is that they don't lose velocity. Okay, so if you have a wall here and a gas particle hit it at a certain speed, like 5 miles per hour, okay, it's going to bounce back with 5 miles an hour, and that's called elastic condition. And the reason why that does is because in the container and the outside world, they can exchange energy. And this is called a closed system, and we'll cover that more later on down the road. But there are three kinds of systems: isolated, and that's where there's no interaction between the inside and outside. There's called open, where there's interaction between outside and inside completely. And there's closed, where there's interaction between the outside and inside in terms of energy. That means energy can pass from one side to the other, but masses cannot move. Okay, so what happens when the gas particle hits the wall? Okay, the outside effectively gives back the same amount of energy that it may be lost, and so it sort of regains its velocity and moves. So we're also going to just assume that they don't accelerate and decelerate. Okay, when they bounce off the wall, they have, so when they come in, what we call the angle of incidence. So if this is an angle here, so it's flying in like this, it's going to fly back off at the same angle. Okay, so this is called the angle of incidence is equal angle of reflection, and you'll learn about that maybe in physics if you take it. Okay, and we really don't want to spend time about it, but it's a good thing to know. Also, velocity is a vector measure, and it has magnitude and direction. So the magnitude is the speed, and the direction is where it's going. Really, we're not going to be worried about the direction. So when I say velocity, I'm going to interchange it with the word speed. Okay, to get an idea how gas particles randomly distribute, you should watch this following video. It's pretty good. It explains that how gas molecules or any random particles actually distribute according to temperature. So let's say you have some gas molecules that are 100 Kelvin, which is really, really cold for us. Okay, the gas molecules are going to be spread out over this blue curve, kind of tight ranging. Okay, but it's still random. Okay, it's not totally random, and it kind of has an average, and it is spread out over a range. Okay, so it looks like this tail goes down to 0, but it actually tails off into infinity. So as you increase the temperature, you'll see that it gets more, and the normal particle spreads out over, have the speed of the particles have a wider distribution of energies, and so forth. So just take a look at this, and this kind of shows that it's not totally random how they're distributed. And they are distributed within a range of speed, given a temperature. And when we talk about the ideal gas law, we'll come back to that. So what we're going to do is pretend that we can get ourselves down and look at small world of atoms and molecules. We'll just call them particles. It doesn't matter if they're atoms or molecules. And what we're going to do is just watch from the outside, looking inside our box. Okay, so you have a box. And inside that box, this box has this volume. Inside the box, there's gas particles, and there's a certain number of them. Okay. They have a certain speed, which I'll call S, or velocity. So they're moving around. And, all right, with some speed, okay, and that speed is the same for all the particles. And then they'll have a certain number of collisions against the wall per given area. So if you were to look at a certain area on side, so if you took, if you looked at a certain section on the wall here, okay, and what you do is you count how many times the gas particles hit that area per unit time. That's what we're going to look at here. Okay, and we'll just call that collisions. And we have six different scenarios where we'll change one of the variables, like volume, and then we'll see how it affects another a variable like speed. Okay, and so we'll always keep two of the variables constant and change one and see how the other one changes. So we have an independent variable that will change, and watch what happens to the dependent variable while we keep two constant. So there'll be 6 scenarios of this, and we'll go over each one of them using our ideal behaviors. So scenario 1 is what we're going to do is take a certain number of, we'll start out with a certain number of particles, and we'll keep the volume and velocity constant. So this box here is going to stay the same size, and the particles are going to move around with the same speed. The length of arrow, it tells me, sort of gives me the speed. Okay, so that the particles don't lose any speed. Alright, and what we're going to do is I'm going to increase the number of particles from 5 to 10, and I want to know what's going to happen to the number of collisions. Okay, well, hopefully you see it's pretty straightforward. As you add more particles, you're going to have it hitting the walls more often, and therefore your collisions is going to go up. Okay, so the number of collisions is going to double from 10 to 20. So there's a direct relationship between the number of particles and the number of collisions, and we're going to assume that it's a straight linear relationship. We'd have there's no. We always, when you look at relationships between two things, you should always assume a linear relationship first. Okay, if it ends up being nonlinear, then it does. But we're going to assume it's linear, and it is. Okay, and the equation of this line is pretty straightforward. The number of collisions is equal to the slope, which we'll call K1, times the number of particles. All right. Now K1 is is specific for the slope of this line here. Okay, or this relationship between collisions and particles. So this is called directly proportional, because it's you change C and as you change N, the collisions change in the same direction. All right, scenario number 2. What we're going to do is change the speed and look at what happens to the number of collisions. Again, our box is going to have this time the box is going to have the same number of particles, and it's not going to change. So you have your box, and that box is not going to change its size, either particles. So we put in 5 particles here. All right. But what we're going to do is we're going to start with a velocity of 4, okay, and then we're going to triple the velocity to 12. And what we want to do is know what happens to the number of collisions. Okay, hopefully you see, as I said, because they're moving faster, they'll hit the wall more often, and so therefore the number of collisions change as the velocity changes if you keep the number and volume constant. And again, we get another linear relationship, okay, where the slope of this line here we'll call K2. Okay, it's different than K1, and it's empirical. You have to figure it out. So we have this simple relation: the collisions, number of collisions, is equal to K2 times the speed, where volume and number are constant. So we have 2 equations already that tell us behavior of gases. Scenario number 3, what we're going to do is now we're going to start out with our box, okay, so maybe size 4, and then we're going to double the size of our box. All right. Okay, the number of particles is going to be 5 in each one, and their speeds are going to be the same. Okay, what's going to happen to the number of collisions if you increase the size of the box? Okay, so if you notice, when you do that, it's going to Now the sides are further away, and it's going to take longer for the particles to hit the wall at the same speed. So what happens to the number of collisions? The number of collisions go down by half if you double. Okay. Now this relationship is an inverse relationship, okay, where as you increase the volume, the number of collisions come down. Okay. And so this equation, because it's inversely proportional, so if you increase V, the volume, C will go down. So for instance, if you had number of collisions, we'll just say K3 is 1. So yeah, K3 it's K3 over 10. That's your volume. Okay. All right, and then scenario number 2. Okay. Let's say you increase the volume to 20. All right, you can see that C goes down. It goes from 1/10 to 1/20. All right, so in this case it's 1/10, and then the number of collisions goes from 1/10 or K over 10 to 1 over 20 or K over 20. So the number of collisions go down, and so you have this relationship here. Okay, it's not a straight line, okay, and that's because of this relationship. Okay, scenario number 4. What we're going to do now is we have the next 3 are going to be related to pressure. So what I have is I have a certain volume, and I have 5 particles. All right, in each one. Okay, and what I'm going to do is so this has a volume of 5, and this volume these particles have a velocity of 4, and these have a velocity of 8. All right, so what I want to do is keep the number of collisions constant. Now, if I keep volume constant, all right, the collisions would go up, all right, from scenario number 1. So if you increase the velocity, okay, and you kept the volume constant, the number of collisions go up. But what we want to do is we want to keep the number of collisions constant. All right. So what we have to do that, we have to increase the size of the volume. So this increase in velocity can be retracted by the increase in volume. All right. So if I speed these guys up, all right. So if they go from 4 to 8, okay. All right. The bigger volume will cause them to hit the wall at the same speed as they did when they were at 5. Okay. So to keep the number of collisions constant, while change the velocity, we need to make the volume bigger, so it takes it longer to reach the walls. And again, we get a linear relationship. So as you increase velocity or speed, okay, the volume has to increase to keep the number of collisions constant. So as speed increases, volume increases. All right, and that's this has some K that's related to and it's all related to this relationship, and it's directly proportional. Okay, scenario number 5. What we're going to do is we want to keep the number of collisions constant. But this time, what we're going to do is increase the number of particles. Let's say from 5 to 10. Okay. All right. Okay. So what I want to do now is, what do I have to do to keep the number of collisions constant when I increase the particles? Okay, similar to the last case. So if you start out with, these particles, okay, and they're all moving at some speed. All right. And then if you add more particles, that's gonna increase the number of collisions. So how can you go against that? What you do is you increase the volume, okay, and that'll make the particles, more particles. It will make them longer to reach these sides. So now, so as you increase the number of particles, you have to increase the volume to keep the collisions constant. Okay. All right. So what you get here is a similar relationship that we've seen for several of the 4 of the other ones. And so if you increase the number of particles, you have to increase the volume to keep the pressure constant. Okay. Right, and this has some K as well. That's specific for this relationship, and it's also linear, directly proportional. Okay, so that's 5. And the last one, again, we want to keep collisions constant, but this time we're going to change the number, and what we want to do is, and we're going to hold volume constant. So what I'm going to do is I have a box, okay. And that, whoops, these boxes should be the same size, okay. And the particle's going to have, so you want to have the same number of collisions, and what we're going to do is we're going to increase the number of particles. So let's say I start out with 4 particles here, and I increase it to 8, okay. Now, we've seen in the past, it's if the you have the volume constant and you increase the number of particles, the number of collisions will increase. So how can I keep the collisions constant without changing the volume? And that's changing this velocity. If you were to slow down the particles, it'll take them, when you add more particles, you essentially slow each particle down, and instead of hitting twice as often as if you were doubling the number of particles, you keep the rate the same. Okay. So if you increase the number of particles to keep the number of collisions constant, okay, the speed will have to decrease. Okay. And so this is an inversely proportional relationship, like we saw with volume and collision. And so you have this relationship here, where the speed that the particles is dependent on the number of particles to keep the collisions constant. So if you increase the number of particles, you have to slow them down to keep the collisions constant. And there's this case 6 is what's related to it. Okay, so that's the 6 scenarios. Okay, and we'll go over them in a second again. But so that's it. And so that's what, if we were to get ourselves really tiny and look at the molecular level, that's what we would think we would see if they were idea. But we can't do that. We can't get ourselves down to the tiny, tiny world. And so what we do is we have to look at, we can't look at the same variables all the time, and we'll look at that. Okay, but before we go any further, I want to look at these 6 different equations, and and rearrange and put them together. And each slope is given as K1, K2, and so forth. All these guys can be put together into one giant equation. Okay, so if we manipulate these guys and where we put all the k's together, all right, so we're going to have all the k's on one side of the equation and variables on the other side. And then once you get all the k's on one side of the equation, you can just call that one constant, because a constant times a constant is a constant. So if you mess around with this, you can get the following. You get K1 times K2 times K4, and you don't have to do this, just showing you. You can try it if you want. Times K4 divided by K6 and K4, you get C times V times N times S over NS V. And when you do that, you get, so you're left with collisions on the top. Okay, volumes cancel out, and you're left with a volume on the top. Okay, and on the bottom, one of the numbers cancel out, see, and with N on the bottom. And on the then the speed, you'll end up one of the speeds on the bottom. Okay, and so you end up with this. All right, and so what we can do, we can call this thing here, we're going to call it little r, and it's going to equal to this over here, CV over NS. Okay, or the collisions times the volumes equal the number of particles times the speed. Now this is a big deal, and we'll get back to it in a little bit. Okay. All right, now what we're going to do is look at the human world, the macro level, I call it. So what we looked at the atomic world or molecular world, and we could call that the micro level. In our human world, we want to be able to measure the gas properties. But few of these variables we can't, are impossible to measure. So we're going to take a look at each one of the variables to see if we can measure it at the molecular level, and if we can't, is there another way that we can measure it? So let's look at volume first. Volume is pretty straightforward. It's three-dimensional, and whatever units you have for it will always be the same at the atomic level or the macro level. Okay, so volume is volume, and it's easy to measure. So volume we can keep at that as the same at both the macro and micro. Okay, the velocity of the particles we really can't measure. You can't go down there and take a radar gun and measure how fast they're moving. But if you go back and look at I asked you to look at that video about how gas particles are distributed, is that the speed of a gas particle is dependent on its temperature. So if you go back, you'll see that at 300 K, sort of the averages of the speed of particles is one range. At 1,000 Kelvin, it's another range, and so forth. So if you know the temperature of the particles, you can know its velocity by using what is called the Boltzmann's constant, the guy that actually came up with those curves. And I'll call it B here. It's typically just given as a little k, but I don't want to get that mixed up with all the other k's. So, and you don't have to know this formula. Basically, you have to know this, is that velocity or speed is dependent on temperature. Okay, so instead of measuring the speed, what we're going to do is measure temperature. And if we really needed to, we could figure out the velocity. But what we're going to see is instead of speed, we're going to be using temperature at the macro level. Okay, the third thing is N, the number of particles. And again, that's impossible to measure. We can't go down to measure at the atomic level. There's just so many particles in a given volume, because the atoms and molecules are so small that we can't do that in reality. But But one thing we can do, and we'll show this more specifically when we get to stoichiometry, if we know the mass of the particles, we can know how many you have. Okay, and as you may remember, that has to do with moles. So what we're going to do is we won't be caught just looking at naming the numbering the molecules like one atom, two atoms. We'll be looking at them as a bunch. So if I say I have 5 moles of atoms, okay, and then increase that to 10 moles, all right, I will be doing that instead of saying I have 10 atoms and exchange it to 10 atoms, all right. Now, so mole is just a huge quantity, 6.02 times 10 to the 23rd. So you would have 5 times that number and then 10 times that number. You don't even have to worry about that number, but you know, the one thing you do know is the number of particles has doubled from 5 to 10. Because the gas that we're going to be using for now all have the same mass, you could also measure the amount of particles by knowing its mass. So since all the gas particles have the same mass, so if you have 10 grams of a gas, okay, not grass, and double it to 20 grams, okay, you would know you doubled the number of particles. So I will be using the moles, but if we're just dealing with a one particular type of gas particle, then we could use mass as well. And the fourth one is the collisions, and it's impossible to measure the collisions per area per time in our macro levels, so we have to figure out how that relates, just like we did with temperature and velocity at the macro level. All right, so what we have here is the collisions per area per time. Okay. Now you could rewrite that. You could write it as collisions per time per area. It's going to give you the same. It means the same thing. Okay. Well, it doesn't exactly mean the same thing, but you don't have. It's the same mathematical equation. All right. So when something collides with something else, momentum, and the number of collisions can be looked at the sum of the momenta of the particles, or m times v, or mv. So what we can do is we can replace this right here as number of collisions with the momentum, okay? Because collisions give momentum. All right. So what we can do is, like I said, you can rewrite this equation as collisions. All right, collisions per time per area. Okay. It's no difference in terms of the math. Okay. So what we're saying is how many collisions happen per time per area, which is slightly different than saying the number of collisions per area per time. So we just arrange it. So now we have number of collisions per time per area, or momentum per time, mv times v, so x is times, or what we can do is we can wrap this guy as m times vt. Now, if you've had physics, you know v over t, the change of velocity per time, is known as acceleration. So what we have is this part here is mass times acceleration, okay, per area. Okay, now again, if you had physics, you learned that mass times acceleration is equivalent to force. All right, and so what we got here is this right here, this guy right here is simply force. Okay, so what we have here, now we have that collisions per time is, so this is force per area. So force per area. And this is the definition of pressure. And pressure, if you in physics, you would learn that pressure is equal to force per area. And I don't want to go over that a whole lot, but the more force you have for a given area, you have more pressure. Okay. Well, we can measure pressure. Okay, we have, you can measure pressure of gas. You just have I'm not sure what that's called, but your pressure valve that you measure. And so we can measure pressure. And when we measure pressure, what we're really doing is measure the collisions. So we're not going to be using number of collisions anymore when we talk about the macro world, just like we won't be talking about speed. Instead, we talk about temperature. When we talk about collisions, we'll talk about pressure. All right, so if we look at the two worlds, we have the molecular and macro world. We have volume, and humans, our world is also volume. Number of particles, we just know number 1, 2, and 3. We can do that at the micro level, but at the macro world, we have to measure them in terms of moles. At the micro world, we measure the speed, but we know there's a relationship between speed and temperature. So instead of measuring speed, we'll measure temperature. And at the micro world, we'll measure collisions, but because there's a relationship with collisions and pressure, it's a lot easier to measure pressure. So what we're going to do is we're going to change our 6 different relationships, instead of using these guys here, to using these guys here. And that's what we get over here. Okay. So here's the micro world. We said that the number of collisions is equal to some constant times the number of particles. So if you increase the number of particles, you increase the number of collisions. Well, at the macro level, that's if you increase the number of particles, you increase the pressure. When temperature or speed and volume are held constant. And that discoverer of that law at the macro level, not the micro level, was John Dalton. And it's called Dalton's law of partial pressure. Now this is a way to describe that law. What we will also write it a different way. Okay, the second relationship says is if you increase the speed, you get more collisions. Okay, now that we go to the macro world, says if you increase the temperature, you increase the pressure. And that's called Gay-Lussac's law. At the macro world, we said if you, it's if you change the volume, the number of collisions will go down. So at the macro world, that's saying if you change the volume, the pressure will go down. And that's called Boyle's law. The fourth relationship said if you increase the speed to keep the pressure constant, or the number of collisions constant, called pressure, you have to increase the volume. So in the macro level, it means if you increase the temperature, you have to increase the volume to keep the pressure constant. And that's called Charles' law. Okay, then we said if we increase the number of particles, we have to change the volume to keep the pressure collisions constant. In the macro level, it says increase the number of particles, you have to increase the volume. That doesn't change. To keep the pressure constant. And that's called Avogadro's principle. And then finally, it says if you increase the number of particles, you have to decrease the speed to keep the number of collisions constant. And so at the macro level, it says if you increase the number of particles, you have to decrease the temperature to keep the pressure constant. And actually, it doesn't have a name. I'm not sure why it's not given any kind of part. But so we're not going to really pay attention to it. So what we're going to do is really focus on these 5 guys here. All right. So going back to when I combine all the constants together. so I had little r is equal to number of collisions times volume divided by the number and the speed. Okay, so now what I can do is I can replace these with the macro values. And so instead of using little r, I'm called big R. And so I have C, which is pressure, V, which is volume, N is number of particles, and T is temperature. Okay. And this is called the ideal gas law. And it can either be written in like this, or more commonly you'll find it like this. All right. Okay, where R is the universal gas constant. Okay, so let's take a look at this a little bit more closely, and then we'll get more into how to use the gas laws. I want to show you what this means. Okay, it's not just an equation; it actually means something. Okay, first, PV term can be broken into its units. Pressure is force times area. Force divided by area. Area has the units distance times distance, so what we have is force divided by distance times distance. And you won't have to derive any of this. I just want to show you what happens here. Now what we're going to do is we're going to multiply pressure times volume. So I have, and volume is distance times distance times distance, so I have force, all right, times distance times distance times distance. So this is, so pressure is force times distance times distance, and then this is the volume term. And when you do that, these distances cancel out, or you get force times distance. Okay, in physics you learned that force times distance is related to work and energy. So this term here relates to the energy of the particle. All right. So what this equation up here tells us is the amount of energy there is in a given amount of particles at some temperature. Okay. So that Boltzmann distribution we saw, okay, would it look like that? It's one temperature, like that is another temperature, and like that another temperature. Okay, is because of this relationship here, because the energy of the particles, or the speed in a sense, okay, is going to be related to the temperature. All right. So it turns out that since gas particles are essentially random, any random particles are going to have this relationship. All right. So R can actually be any number, and it can be a number depending on the units we B and U going to be used. Now, one of the things I want to show you is, just sort of relate you to, is that we talked about Boltzmann's constant before. You know, what temperature equals Boltzmann 2/3 Boltzmann's times the velocity of the particles. Okay. Well, R is really just Boltzmann's constant times Avogadro's number. So essentially R is how gas particles are distributed at a given temperature. So that's R determines the shape of these curves here. Okay. And we'll see this again at some point, this relationship of Boltzmann's. But this is just, I just want to let you know, when I learned about this equation, I just saw it as letters. I don't remember my professor explaining what R meant. Okay, so R is basically tells me the energy of the particles per temperature. Okay, and I just want you to know that it's what it means in theory and actually practicality. Okay, so now let's go back to the 5 named equations. We won't be using that 6th one. So what we want to do is rearrange those equations. Let's say we're going to look at Charles' law. So Charles' law was the volume is equal to K4 times temperature. Okay, and what I want to do is change this equation up a little bit more. Okay, and so so let's do, so what I'm going to do is I'm going to change this equation so I can use it in a more practical sense, because we really don't want to figure out what K is. Okay, so let's say I have a certain beginning temperature T1, and I want to go to change the temperature T2. What I want to know is, if I start out with a certain volume, what will be my new volume when I change the temperature? And it'd be nice, what you could do is just say you could figure out, you know T1, you could figure out V1, knowing if you have K4, and then you could figure out V2 because you know K4 and T2. But let's see if there's another way of doing it. And so what we're going to do is do this. So so let's say I have 2 points. I have V1 and T1. That's my starting, where I have initial volume, initial temperature, and then I'm going to change the volume and the temperature to some new values here. And remember, it's linear, so I have some point here. I'm going to change it maybe to that point here. So this is V1 and this is V2. All right, so the slope, so we'll just go back, basic algebra. The slope of this line here, K4, is equal to V2 minus V1 over T2 minus V1. And that's the definition of a slope. So this is the Y component, and this is the X component. So volume and temperature, okay? All right. And then what we want to do is we're going to replace K4 with this equation here. So what we do is we rearrange this equation. K4 now equals V1 over T1, or you could do V2 over T2, but we're going to use V1 over T1. So I'm going to substitute V1 over T1 for K4. That's a simple algebra. So now I have this. Okay, and then I just cross multiply, and I get multiply both sides by T1 and T2 minus T1, cross multiply, and I get this. Alright, and then I multiply all the way through, and my V1 and T1 all the way through, and I get this. And if you notice, is that I have V1, T1 is the same on both sides, and so what I left is with this. Okay, now what I have is an equation that looks at the relationship between V1, V2, and T2, T1 without involving K4. Okay, you can rearrange that as V1 over T1 equals V2 over T2, or T1 over V1 equals T2 over V2. All right. Okay, now we can do the same thing for each one of the other equations. All right, and so we'll show that in the next slide, where we get rid of the K's and just end up with our initial and final. Okay, so Charles' law was like this. Okay, and we could rewrite it like this. I can do the same thing with the Gay-Lussac's law, and then you end up with this. And then you can do the same thing with Avogadro's, and then Boyle's. Now notice is that Boyle's is different. Notice Gay-Lussac's, Charles, and Avogadro's is that when you do the multiplication version, P1 T times T2 equals P2 times T1. Charles' law is T1 times V2. But when you, and Avogadro N1 times V2, but when you look at Boyle's law, the numbers are on the same side. P1, V1 equals P2, V2. Dalton's law is actually not written similar. It's written as the number of particles, total number of particles is equal to the sum of all the total pressure is equal to the sum of all the pressure. And that's because this should be N total is equal to the number of particles of one gas times the number of particles of number 3. And so what this is saying is that if you increase the number of particles, you increase the pressure. And then there's another law that combines Gay-Lussac's, Boyle's, and Charles' law. It's called the combined gas law. Okay, so we will be looking at these 5 laws, using them for doing problems, as well as this guy here, and the ideal gas law. Okay, now what we're going to do is go to look at another law, and that's look at Graham's law. Okay, we said at the very beginning that all the gas particles have the same kinetic energy. All right, they all have the same momentum. Momentum and kinetic energy are related. So, momentum is m times v. Kinetic energy is 1/2 times mv squared. So, if momentum is m times v, and kinetic energy is m times v as well, then if you conserve momentum, you're going to conserve energy, kinetic energy. All right. So we also said all the particles are the same kind, but let's expand that and say that we have different types of gas particles here, and let's say I have some carbon dioxide and oxygen, and what I want to do is compare their speeds. Okay. Now, so okay, so we said that all the gas particles in a container will have the same energy. So these 2 particles will have the same kinetic energy, right? But the difference is that they will have different masses. Okay, so this would be maybe kinetic energy 1, kinetic energy 2. Carbon dioxide has a mass of 44 grams per mole, and oxygen has a mass of 32 grams per mole. So this guy is heavier, okay, than the oxygen. So to keep the kinetic energy the same between these two gases, what you have to do is this gas here has to actually move slower. Okay, and what we can do is come up with the relationship between the how fast one moves compared to the other, depending on their masses. So this guy's going to move slower by some relationship between 44 and 32, but it's not, it doesn't move 32 over 44 as fast as oxygen. We have to be a little bit more careful here. So the kinetic energy, total kinetic energy of gas 1 has to equal the kinetic energy of gas 2. So what we have here is these 2 equations equal each other, so that the halves cancel out, so you get. All right, now if you separate them algebraically, you get MA divided by MB equals VB squared over VA squared, or you could just say MA over MB equals square root of VB over VA. All right, sorry, I meant squared. Okay, so anyways, so what you can do is you can rewrite the equation here, is that the velocity of A over the velocity of B has to equal to the square root of mass over mass of B over MA. And this is called Graham's law of fusion. Fusion is how fast the gas molecules or particles can move through a small opening, like when you have aerosol can and you spray it. How fast do those particles move through? So if you had, for instance, oxygen versus carbon dioxide, the oxygen would fly out faster out of the nozzle than the carbon dioxide. Okay, so that's kind of interesting thing there is that you kind of can relate that to I don't know if you ever have seen or have done it. If you take some helium and you breathe it in, your voice goes high. All right, so why does it go high? All right. Well, in a sense, when you breathe or when you talk, what you're doing is you're passing the gas is moving through a small opening, your larynx. All right. So helium is really, really small, so it moves fast. Okay, so it moves faster than air, which you normally breathe, and so you're going to have a high-pitched voice. Okay. On the other hand, let's say, I don't know if you've ever done this, but you've seen people that do it, but they belch the alphabet, and it's low. All right. Now the reason why it's low, okay, is because carbon dioxide is heavier than air. And so as it moves through your larynx, it moves slower, and then you have a deeper voice. Okay, at this point, we've finished this slide and the slideshow. And what we will do now is there'll be 2 more slideshows that have to do with gases. Next one will have to do with units. And what units we use in gas laws, the pressure, temperature, volume, and number of particles. And then on the last one will have be some problems that we use the gas laws. And then there will be worksheets on how to use the gas laws. Now, what are you going to have to know from this hour of material that we've gone over? Well, really the main things you're going to have to know are the gas laws. All right. You're going to have to know the assumptions of the ideal gas law, as well as we talked about at the beginning, and what how collision and pressure are related, and how temperature and speed are related. And so you'll have Charles' law, Boyle's law, Avogadro's principle, Gay-Lussac's law, Dalton's law of partial pressures, combined gas law, and the ideal gas law, and how to use all of those, and how to recognize them, and how to use them. So if I were in class, this would have been a lecture, a class lecture, and so let's move on to. So I'll see you in the next one. I have to do with units.